endurance 50-hour plus, and mapping. There's support for multi-vehicle operations, and you have over 80 LAUVs in action worldwide. This is because of our spin-off, Ocean Scan. The operation is quite simple. Endurance 50-hour plus, sure, and mapping. There's support for multi-vehicle operations, and you have over 80 LAUVs in action worldwide. This is because of our spin-off, Ocean Scan. Source software. The operation is quite simple. Endurance 50-hour plus, sure, and mapping. There's support for multi-vehicle operations, and you have over 80 LAUVs in action. This is and then you have our spin-off, which you can do exactly the same thing. The operation is quite simple. You can have software enabled such as there's a spin-off, as I told you, Ocean Scan is in selling, and then you have our spin-off, which you can do exactly the same thing. The operation is quite simple. And this picture is quite relevant. The LAUV from the page of Science Robotics, and it was announced together by our friends from Agar. I would also like to reveal this project. We have several other projects, but this one is very special for what we do. This is an infrastructure project. X20, 15 partners, and most of these players in radar robotics. And what is the project about? So, three main things. One is to provide access for free to our infrastructure. And you see some of these here. So, people can submit or submit proposals to the infrastructure, and what is that? Handle regulation, and we had over 50 transnational access projects through the infrastructure. We also worked on making this operable and high specialized training, large-scale experimenters, worldwide operation, and interactive just to give you a sense for the footprint in terms of GNA access, transnational access. In blue, you see locations of partners, and yellow, green, and red, you see locations of institutions that successfully applied to use our infrastructure and successfully demonstrated their growth. So very real. Now switching gears and going into operations. We've been operating in lots of different places. We've been organizing large-scale exercises from shore, ships, and also from land submarines. It's quite unique. Typically, we have over 100 days of operations per year, and I don't have the figures here, but from 2018, we have over 4,000 kilometers underwater and over 200 flights per hour. One example, simple but quite relevant, mapping the boom of the river, so the river goes into the ocean, there's fresh water, kind of ocean water. You can spot the booms from here, but we also have the people that kind of map the booms as it moves. And what you see here is a representation of one of those missions. So you can track my pointer, this is the kind of boom, and then you can spot the water kind of performing these transects, zigzagging along the boom. If you look at transect 1 here, you can see salinity plot, so you can fresh water at the surface, and then again salt water, salty water here. So, and by doing this, you have a very interesting characterization of the boom. This is very interesting for marine sciences, for biology, and actually there's also mechanisms for the generation of internal waste. And then again, nothing completely different that we use about the electricity, doing it rep exercise that we cooperate with Portuguese Navy, also our friends from Ingin and other aims. So we have multiple assets employed offshore and rest from the Portuguese Navy. And the idea was to attract whales that have been tagged, and at the same time, while we're doing that, measure environmental parameters for the whales. So this was done with the help of the planner, one on board that passed multiple assets, and then another planner on board each vehicle that will take care of the track for whales. Without going into details, it's fast forwarding operation. So what you see here is the UAV flying and trying to find the whale, and at the same time we have the UAVs in the water measuring environmental parameters for whales. Another example would be more complex. This took place in the RAP exercise in operation in Portugal. So we have Berhenti, surface vessel from the University of Hawaii. We also have a seabed node from the University of Hawaii. And then we have the UV from the Laboratory Work Center, the gray ones here, and the UV from Port University, the LAUV. And then we also have this exotic flying modem that I performed, the helicopter that can take off and land in the water. And this is how things work. So the operator will send mission commands to Bantu that have a communications gateway that will forward these mission commands to the UVs. And then, or the operator should send the mission command, mission plan to the flying modem when this was within line of sight. Then the flying modem will land close to that node and then send a message to that node, mission plan command, and then the UVs will go by the that node, the mission command extract the mission plan, the flying modem, something else. And again, these are just a few examples. Optimal activity rest and other forcing. So the best gravity, very strong currents there. And then we have a high res model of the current with approximately 5 million points spread in space, time. And the question was when and when to deploy an LED to reach the target or target representation like the dot in minimal time while staying clear of high res. So we have a very elaborate approach based on dynamic programming on numerical methods called beneficial Hamilton-Jacob development equation. And what you see here is one example of the experiment. The length is 13 kilometers, 3 hours. Velocity gain because of the current was 15%, and the difference in what people did and the estimated time of arrival was 2 minutes. And there's much more to read, but I'm not able to one example based on experiment for the length the audience 13. Something else that was also demonstrated in the graphic exercise 2018. So we have AUV and ASP, we have one operator, and we have system level planning execution control, for example, for coordinated mapping. Here's an example. First of all, these guys will perform something else, the nation control, and then we'll switch different calls, which is a kind of a cooperative mapping, coordinated, in which the AUVs were tasked basically to map different areas, and then use some tools, and those guys will retask using defaults without any human intervention. And then we'll switch another different achievement was the implementation with physics. It was funded by the Leadership Institute. So 3 weeks on board the RP Falcon, and our team, so we have people from, again, our friends from NTNU, from the Universities of Rhode Island, University of Harvard, and we also have collaborators from NASA, from Portuguese Navy, and SINCAP, and basically we went after the Northern Pacific subtropical front to demonstrate a novel multi-vehicle system capable of finding, tracking, and sampling features of the ocean with adaptive spatial and temporal collaborators from NASA. So here's the video. I hope you can hear the sound. And basically This was approximately 1,000 nautical miles west of San Diego. So this was the system architecture. So we deployed from Falcor. We had some very nice set phones. We interacted with all of the assets using set phones. And then we had a Ripples, cloud-based system to support all of our operations. So we had a control center in Port and another one on this was the Falcor. We operated non-stop for shifts per day. And this is kind of a picture of the mission control center in Porto and mission control center to support Falcor. Just to give you a sense for some of the things that we had. So in the background you see a sea surface temperature map. So red means kind of higher temperatures and kind of a picture of lower temperatures. And then superimposed on this you have tracks of AUVs colored by salinity. And there's a very interesting correlation between the sea surface temperature tracks. Keep in mind there's also a time shift because this mathematical map approximately when you read 50 nautical miles by 40 nautical miles, it's still very interesting. We learned a lot. We had our simulation performing automated front detection and tracking. We also performed high resolution radiation sampling, which the Falcor and UAVs when you need information to provide a geologic field of the ocean in that area. We had our simulation performing automated front detection and tracking. We also performed high resolution radiation sampling, so basically we were extending the footprint of what the ship can provide. And then again we know from Eric Schmidt, technology first, new technology should drive the SY science program. Accomplishments. So we successfully demonstrated an umbrella approach to observe the ocean persistent and with systems. Operations, we operated for a long time, and systems and technology demonstrated that these proofs are also applicable accomplishment other areas of the approach where we observe the ocean persistent. Now, finally, let me briefly discuss future development operation from the vehicles on site. And this one goes from Berhenti and other colleagues since around 78. And they said they don't believe that existing mathematical tools are powerful enough to define a practical structure for decentralized future development or hierarchical controls. And the fact is, this is still a challenge. What are we talking about? So if we look at all of these different missions and operations, we can try to come up with a taxonomy, which is not very formal, just kind of a conceptual way of discussing. So we could think about classification in terms of number of methods, vehicle and function in 90, deliberative planning on board, dynamic teaming, mission complexity, built-in resilience, cause-based interactions, communication, cost of losing an asset, logistic support, interoperability, and persistent functioning. And you see that some of these cases are like mapping, so very different here, but we still are facing lots of communication challenges. And another important observation is that we are not talking about swarms. Apart from that, it's notion of we can discuss this later on. Another important observation is the notion of dynamic reintegration, which is a common feature of communication systems. The notion of link not as a fixed part of the system, but as a data that can manipulate, it's essential for understanding such systems. And so we need to evolve the notions like value, relation, function, to make it evolve from which is a common notion into those of links, interaction, and process. It's a code from Robin Milner during Award in 91. And another important thing is the notion of mobility, which is quite common in the software community. I won't go into control mobility, visibility, objectivity, but one observation about mobile computation, when you have mobile software that can go from one network node to another network node, and also mobile computing, in which you have mobile hardware that can serve the computational needs of the given situation. And then we also have different models. There were several attempts in the computer science community, one from Robin Milner, which was the idea of Y graphs, which is based on a graphical model of mobile computation that emphasizes locality and connectivity. And then this is very important because keep in mind that you can have mobile software, but you can also have mobile hardware. And this framework, you have the place graph that has a structure of the tree, and the link graph, the cycle graph that basically establishes relations. And when you keep it together, you can describe the state of the system. And then systems evolve through different pie graphs. And then there were pie graphical reaction rules explaining how the system and the link graph still is proved to be very complex and at the same time very good. And just for the sake of reasoning or brainstorming, if you will, think about something different. Think that we have a system vehicle A that moves X and Y. This vehicle has sensors, communication, motion controllers, actuators, physical entities, sensors, and also has a computational environment in which you can have several processes with one algorithm. There could be other vehicles, exactly the same thing, and those would be communication range, communication range, and you can communicate over these, and then if you look at this and if you look at these systems in terms of models, you can get inspiration from the active model of vehicles like car activity. Then we get a long time communication range, but the interesting thing is that these guys are communicating, then you have physical entities, there are vehicles with nicknames, these can be composed and can enable mobile locality, and then we also can have transition functions that depend on physical interactions with our physical devices in the environment, and you can become a physical entity from communication. This is basically describing what we're seeing here. But then you can go one step further, right? Because if you have communications, then you can also use processes or software, if you will, from one vehicle to another vehicle. Then you can compose processes or algorithms, if you will, based on different vehicles, you can have communication. And then you can even go one step further, which is what communication with other assets can form a team. And the team can also have a unique name, you can also have a unique command set, and there will be more communication with different vehicles. And then you can think about, okay, how am I going to go about specifications for behavior of the system? So think about time interval, and you can say that time interval, Tmax will be given region, and equals different region. Then in the next time step, these guys can move to region 5, and then start the dragger. And this will be a sort of a specification for this type of system. Then what will be a run-on system? Imagine you have time, you have space, you have a bunch of vehicles. Region here, another bunch of vehicles. Region here, and then they can other regions, they can then connect, establish teams, then some vehicles can leave teams, go to other teams, and then measure that time. So what are the new challenges? And I'm almost there. So given a specification for behavior of a set of vehicles, synthesize a set of computational entities which decompose their sense with the vehicles to satisfy the specification. So we need a notion of behavior equivalence. And what will be a run-on system? It will be a coordinated sequential and parallel execution of classical control problems for relay computational entities in space. And then you need properties such as continuation, information reachability. So you want to make sure that information reaches what vehicle when it's needed, termination, well formulas, and encapsulation. And some final thoughts. It's tough to make predictions, especially about the future, but in terms of trends, the pace of change is accelerating, low formation of islands, and we need new models of cooperation network, and we can think about the power of networks. Think practical, think big, and think predictions. So thanks very much. But in terms of trends, the pace of change.
Thank you, Professor D'Souza, for a wonderful talk. Unfortunately, we can accept only one question. So if somebody... I think there are no questions. Let me check online. We have few online audience. Yeah, sorry, we don't have any questions. Thanks for your presentation, Professor. Yeah.
Thank you.
Okay, we have there are no questions. Let me check online.
This is not a question, but it's just a note I got from Michael German, co-organizing this conference and director of the REST Research Center, and I know he would like to follow up with you and all the aspects of your presentation. It looks to me like we're going to have like several robots roaming around the streets if you start talking with him. But thank you very much for your super presentation.
Thank you very much.
Director of the REST Research Center, and I know he would like to follow up with you and all the aspects of your presentation.
Yeah, you're welcome.
It looks to me like we're going to have several robots roaming around the streets.
Yeah, our next speaker is an assistant professor in the Department of Computer Science at Dartmouth College and a co-director of the Dartmouth Reality and Robotic Lab. His talk is towards the resilient low-cost robot teams for autonomous and aquatic exploration. I welcome Professor Alberto Culey at Dartmouth College and co-director of the Dartmouth Reality and Robotic Lab. His talk is towards the resilient low-cost robot teams for autonomous and aquatic exploration. I welcome Professor Alberto Culey.
Halo Mas, Assalamualaikum. Kabar baik Mas Ali, apa kabar Mas?
The main difference between AUVs and ROVs is using the tether. And AUVs can be reprogrammed or they can be logically derived. Of course, AUVs can be also linked with the surface. The device can be linked with the surface with using acoustic modem or RF or optical link. Can be reprogrammed. Moreover, AUVs are more used in the military actions or exploring the unknown marine environment. So for going to deep of the Red Sea, we clearly need the ROVs. And the perfect ROV would have the important characteristics such as the minimal tether diameter, very small in size, and high data transmission, high data pipeline for center up. And the perfect ROV would have the first ROVs are actually developed in 1960s, which one you see on the right side by US Navy. And later on between 1980s and 1990s, there was a growing industrial interest. Since then, recently, from the Stanford University, with the group of Osama Hatip, the humanoid robot is released. And later on between 1980s and 1990s, so the communication and control of underwater vehicles is a complex issue. So the basic issues involved with underwater vehicle power and control can be divided into three parts, which is the power source for the vehicle. So the vehicle either can be charged on the surface or it can be charged with the docking system under the sea. So the basic issues. The second part can be the autonomy. So the device can be full autonomous, semi-autonomous, which can be remotely controlled, or with teleoperation. And the final part is the communication link with the device and the surface. So depending on electrical or fiber optic, it can be a hardwired communication or it can be acoustic communication, and the final part via underwater analog or digital with the modem, or it can be optical communication while the fiber optic vehicle is on the surface, or it can be radio frequency communication while the vehicle is on or near the surface, or it can be optical communication while by explaining this, we have three technical contributions with the research centers and between our group. So the first one is underwater communication for multi-robot coordination. Second one is long-term autonomy that defines the robot navigation and the battery life. And the last one that more I will concentrate on my topic today will be the robot and agile control. So the main application that we are looking for is the environmental monitoring that may include the population growth of the organisms, or that can be environmental detection, environmental parameters detection such as temperature, salinity, and moreover, we are also working on a project for the underwater manipulation that you see one of the examples were given by Professor Charlotte Park and Professor Shinji Park yesterday for the color restoration, and it can be also sample collection. Moreover, we are also working on a project for the underwater manipulation. So in 1967, by Louis Armstrong, there was a song named What a Wonderful World. So, and by inspiring from the nature and underwater habitat, I would would like to name this one as what a fractional work as a researcher who is working on this area. So in processing role, more than 95% of the control loops are based on the PID or PID type of controllers. That's why maybe this is the main motivation that can be focused on this topic. So the fractional order controllers are just a more generalized topic than the integer order PID controller. Here you see on the bottom two mathematical equations that describe the integral operator, the fractional integral with a power of lambda, while the derivative operator with an arbitrary order of PID controller. So the main benefits of this type of controllers are they give more degree of freedom, which comes from the arbitrary order, and you can define more smooth responses of the system that gives more robust and agile control. And on the right hand side, there's the generalization of these fractional PID controllers that based on the order can be proportional derivative, proportional integral, or PID control. So the half-order fractional PID controllers, the frequency response is given as here. So if we think about basic trigonometric equations and the Euler extension, we can easily actually get the response of the system. So rather than the classical integer order system in the fractional order domain, the phase response is varying from minus 90 degrees to 90 degrees rather than just staying in this range of the system. So I give a brief introduction about the fractional order controller, but to solve these derivative operators, we need the fractional calculus. So what is the fractional calculus? It is just a misnomer. So we should better define this is an integration and differentiation of arbitrary orders. Is a more appropriate definition. So this is a type of area regards maybe 300 back. This is 300 years back, and it started between the communication between the Lopita and the Leibniz. That Lopita is questioning what can happen if the order of the derivative is half. Later on, there were many other researchers coming out, such as Ben Hadriman, Joseph Lewis, Alexei Letnikov, and Grumov. So from this definition, you can clearly see that the integer order derivatives are surely a kind of special subset of the fractional order derivatives. So if you look from the mechanical and electrical perspective, to emulate the fractional order behavior in the mechanical system, we look the force and the correlation between the force and. So if you look from the mechanical and electrical perspective, for the spring case, it is just proportional. But if you look at the viscous friction and the inertia, based on their definition, they can be defined as the fractional order element. And for the analog circuit theory point of view, proportional. The fractional order differentiation and integration can be defined with the correlation between voltage and current. So in a generalized form, of the mechanical systems and electrical systems of the fractional in the fractional domain, they can have the mass can have the power of alpha while the current is the same. And the alpha should be the real number. However, it can be also complex, but it gives us more complex systems. In the fractional domain, they can have later on there were many more studies, but the very well-known are performed in the beginning and middle of 19th century by Bilim Google and Guru Matlemnikov. So as I said, fractional order control and fractional calculus has a long history back, but there are not much practical applications in this area, especially if you look at the robotics point of view. So here are few examples that I will use. So the first one is hexapod robot. As you see on the top side, the robot body is divided into n identical systems, especially if you look and linear spring and delta systems are just defined on two types of surfaces, body compliance and ground compliance. On the top side, the robot body is divided into n identical systems, especially if you look and the general control architecture of the hexapod robot is presented just at the bottom of the presentation. So the trajectory planning is evaluated in the Cartesian format, but the control response is performed in the joint space. Therefore, it requires inverse kinematic model in the forward lightning path. At the bottom of the base algorithm considers only the position and velocity effect, but the control and the response is performed in the joint space. To improve the response of this architecture, in the feedback loop with information of the foot ground feedback interaction force is required. Of course, in this case, we need to, in order to run the foot force feedback, we need to simplify the G1 and G2. Feedback loop with information of the foot ground. And here it is clearly seen that for the foot force feedback, we need proportional in this case, which is defined as K1, and we need the derivative operators. We need to simplify the G1 and G2. So my second example is from the industry. So recently Stran and we need Stran and Pedro make a study with the fractional order calculus that use this fractional calculus in their suspension system. So my second example is, however, these are the recent studies that don't give much details, but the point is we are happy that the fractional calculus is being applied in the industry. So the last part, the last example of the applications are the marine robotics. So I recently see just one example, experimental example in the marine robotics that uses the fractional calculus. So here, depending on the desired speeding, like desired motion, they are modeling the fractional order control, and the tuning parameters is the cloud-based quantum genetic algorithm. So as we see here on the left-hand side, the figure illustrates the simulate model of pitch angle using fractional order PID and comparing it with the classical integer order PID control. The step response is depicted shown on the right-hand side, and it's clear that they have the same right side. However, the fractional order PID controller is smaller overshoot with the same step length time. The step the disturbance of ocean currents is simulated by white noise as shown as here, and further demonstrated the better performance of the fractional order PID than the traditional PID control. So this was all my talk. Thank you so much.
Today, and we are progressing towards making this operation autonomous. So it's not just having the aircraft in the operation and building the software to manage all this, so that progressively we can take the pilots in the aircraft and move them to the ground and then have them operate a number of aircraft today. And we are progressing, so we are building a teleoperated vehicles. Not just having, you probably have seen a lot of what is called eVTOL, large drones that can take off vertically and land vertically, but they present a lot of challenges. We take a very pragmatic approach, and we want to leverage all of the infrastructure that already exists. So this is a map of all the airports in the US. For instance, we have over 5,000 of them. It's an infrastructure that exists where we can take off and land for free every day. So why start on the roof that does not exist of a building? Let's start on the airport. Then it's, as Jan was saying, let's start like small steps. Right? We make the aircraft autonomous, but then once we have that electric passenger control, so let's take one step at a time. So I'm going to talk first about the automation of the aircraft, and then we're going to talk about the cargo market. So the idea is to bring the pilots or the pilots to the ground, like to a network operating center. So let's take one step to have them connect to an aircraft, load emission pipeline, like where do we go from planet A to planet B, and then have this operator solve some of the real problems. We saw this one in the NLP, it's like a progress center, so ways to be able to use that reliably. So the big question is, do we know, does the automation or the robots not know what it does, right? In this case, air traffic control is a major challenge, so this is something we don't plan on solving. We plan on having people on the ground and talking to behalf of the aircraft and relay this information between air traffic control and the aircraft. So the big question is, do we know, so the aircraft, we start from this aircraft, so it's the workhorse of the industry. There are 70,000 of them around the world flying all types of missions, either passenger or cargo. It's a simple aircraft relatively, so that's why we started with this one. So you have like simple cables pulling all the technical services, and we are adding our system to manage the engine, to manage communication, to also do airborne and ground threat detection. That's the key piece. We heard earlier about the beyond line of sight side. The only way to do that is to have what's called detect and avoid system, a system that can detect any type of threat and safely route the aircraft. There are 10 out being developed for this, and we are actively working on one of the systems. And of course, the system has to be fully redundant in case of failure to be able to configure and perform the mission. I have another video that shows how we do that in practice. So this shows
Control is ready for ground block. Elevator neutral, aileron coming left. Deploy is complete. All systems go, ready to taxi. Control ready. X-Wing Caravan, TSA, ready to taxi, one left for takeoff with information mic.
X-Wing Caravan, conquer ground, runway 1 left, taxi vehicle.
One left, main ramp to guys, X-Wing Caravan, ready to taxi. X-Wing Caravan,
For the sake of time, I'm going to stop here. But like it takes it back to the end. The videos are meant to be shown and watched to the end. But basically, like at this point, we have a three-golden select what it takes to integrate the airspace. What we have, so we have the Unity station. In this case, we have 113 autonomous flights, 302 auto lands, and by repeating that, the videos kind of like what you have to do. Like every time you go fly, the default can ask you something basically like that. So those are the type of things that we want to learn, and that we also learn by using our continuity sites or like our airline where we get all the feedback and like that. So lots of milestones. This is not a train of autonomous counts, like miles like what we can do and fly for days, and we have nothing to learn. What we learn is by pushing the boundaries and going to fly into new places. And that's but at the same time, every time we go fly, we get all the events that happen. We make sure that we can account for them, or that we improve our logic to be able to handle it. We can do at this stage, what you've seen is a prototype, and we are moving towards the certification system. So this prototype has like a system of pilots. We have 3 axes, the throttle plus the braking and the gate missions that you've seen. We have architected an avoid system that I'm going to talk about after that. It's coupled to the autopilot, so you can automatically route when it flies. Well, this chart is not dated, so it's more than 300 autolands also take off at this stage. Our longest flight is 840 miles, 4.2 days. That shows that the boundaries. This aircraft is able to go 1,000 miles, like 1,900 kilometers. So we're not talking about like your 300 miles flight, but take off and go, be able to go really far. So that pushes us to realize that what kind of communication system do you need to be able to talk to the aircraft throughout the journey. What latency we have on satellite communication network? What kind of communication we need at the airport? So it's the airport is able to integrate into a dense traffic. And we are able to do remote operations on the ground. And a lot of the planning also is we have to be quick. It's not that we get authorization from the air control. We have to speak and get that translated. So we have ways to translate really quickly when air traffic control tells you like which sequence of taxiways to use, that opportunity path that is checked and feasible. And if the aircraft is taxi, it takes the object stop and has to be routed. To give you the research community some engineering challenges. So they're not like science trying to be solved, but like challenges where it's the remaining 20% that we have to solve. It's difficult 20%. So hazard avoidance. So when you're flying, be able to detect other airplanes far away, discern them from trucks on the ground. It's a very difficult challenge. That's a place where there's still not a single solution. So integrating the radar and integrating to go at the time. Ground detection avoid. When we do the flying, solving the self-flying, we self-drive them from. We have to drive on the airport. There are other cars. We have deals. We have animals that can be on the runway. So we have to be able to detect and to avoid all of these hazards. The certified navigation. GPS is great, but not good enough. So we need to have the precise positioning for taxiing. We need to be able to follow the center line. We don't always have the center line. So how do you make sure that you're not going to get out of the runway and hit your prop into the sign on the side? Certified navigation. Ways to guarantee that the GPS based on command that you're not going to that you're landing on the runway. You need to be able to detect an error on the GPS with auto details. And auto takeoff is pretty trivial most of the time, except the heading in that case might be out of the runway. So do some things where we don't have CFA or ES that doesn't have a certification base. You don't have regulations that tell you exactly what to do to be able to certify it. And hazard avoidance, there is no regulation. Flight control is a solved problem. Now it's the time of making it affordable. You go to Boeing, Airbus, they have highly reliable flight control system, but they're just way out of price for projects like ours. So it's not going to be viable if we have to use one of the systems. And then communication. We need to be able to communicate with the aircraft for long distances and have some level of reliability and guarantees on this wasteful command control. So it's not going to be viable. It's like videos. This is an example, not like you and Apple, but of our detectable system. So in this case, we are using 4 cameras. We also have ADS. In this case, we are flying with another aircraft like head-on encounter. So it's a very complicated for like videos. So this is our test pilot, and this shows like the measures in real time. If we get to this location, we're going to have to be too close. So the aircraft, in this case, we're using one of the sensors called ADSB. Then we're going to detect with the radar. In this case, it's going to read that get to the yellow. And then we also have the camera that are tracking this aircraft. So we are using multiple sensors to validate one sensor gets another. So in this case, the radar will be shown. In this case, you have like all the parameters. So get to the right. So slightly violated the separation distance, and we're working on making that better. So next time I'll have sensors to the SAD. One sensor gets another. So in this case, perception on the ground. So now that we solved the price in the air, we have to do the same thing on the ground. So we need to avoid, as I said, many types of obstacles. So in this case, we are using LiDAR. Right now, probably the best sensor for this. So the top is the raw point Service Cloud, just at the bottom, when we discussed using Voxel, and that's the question I had yesterday, to avoid, as I said, model obstacles, and to safely, in this case, it's really like we see something that happens, it's mostly about making sure there is no undetected objects that we safely stop when we have yesterday. The nice thing about being in the Silicon Valley is that you have autonomous or self-driving cars and everything else all over. It's a great place to hire time. It's mostly about making sure there is no undetected objects that we developing drones takes a lot of manpower. Lots of people make one aircraft fly. Drones usually it's 20 or 30 people to get one aircraft airborne. What we're doing it with optional piloted aircraft. So we have a safety pilot in the left seat. So that allows us to fly wherever we want almost. It allows us to integrate the airspace and have very few restrictions. So it's a really good approach to get started to experiment and to integrate that airspace. So we have a station in the back of the aircraft, so we can set aside the issues of the command control link. So we have our engineers sitting in the back, monitoring the system and can put as needed. And then on the right hand side is the ground control station. So you have the same display as we have on the aircraft. We relay some of the video for the detection and avoid system, and then some of the other videos are more for situation awareness and are not required for operation. So we have, the objective is to fuse all this information to a single screen such that eventually that operator doesn't need to get can handle multiple aircraft. So it's about providing the right situation awareness and not required for operation. So we have, the objective is then what primary information to bring back to Ing's question that eventually that operator doesn't need to. What primary surveillance, like why we can handle this problem? Eventually the market of regional transportation is huge. People want to travel long distances for like a low price and short time. So we're solving the regional transportation problem, and we are tackling that by removing some of those barriers to entry. So we start with like low passengers. Let's start with an aircraft that is known, that is works really well, that is simple, and focus on the automation. Let's solve the automation problem first, and let's do that for cargo. Lots of places around the world where the distance to go to some communities is really long. You have to drive, sometimes you have a body of water in between, you have to drive like 15 kilometers because there's no bridge. If you fly 5 minutes, an hour flight, an 8-hour drive. We get emails regularly from people in northern Canada where they have cities that villages are isolated and they don't get supplies. They don't have a pilot. This is an airport, you have an airplane, they don't have a pilot. So there's a huge pilot shortage that the COVID enhanced. And lots of pilots are retired. And now it's really difficult for the small cargo aircraft to find villages are isolated pilots and they don't get supplies. They don't have a pilot. This is an airport.